Hello everyone, this is Reza Wazi, and in this tutorial you are going to learn how to conduct cross-validation analysis using RapidMiner. As with previous tutorials, I have already imported the data that we are going to use in this tutorial. So we are going to use the dataset that we used for the previous tutorial, the neural nets tutorial. So we will use the neural nets training, and remember, in the validation or performance measurement type of analysis, you are always using your training dataset, the dataset that contains your label variable or your target variable. Okay, I dragged and dropped the training dataset for neural nets. Let me change its name to NN training. So you know it's the dataset coming from the neural nets. For the good data understanding and organizational understanding, I advise you to watch the neural nets tutorial one more time. Okay, for this analysis, it's a cross-validation analysis. It's a sort of validation analysis or performance measurement. Then instead of simple split, we are going to split our samples to k parts. Use k minus 1 parts for training and 1 part for testing, and then repeat this training and testing with all the data parts, with all the data partitions, until we have used all these partitions as a testing dataset. Let's go ahead, search for cross-validation here. You go ahead and drag and drop it. It's under the validation. You connect the training dataset into the cross-validation. And then you can see here that this is a multi-level operator. This is the first time that you are seeing a multi-level operator in RapidMiner. So whenever you see this sign, that indicates it's a multi-level operator, and there is a sub-level or sub-process to this operator. In order to get to the sub-process, you need to double-click on this cross-validation. It will take you to the sub-processes. On the left, you have the training, and on the right, you have the testing. So on the training, you want to use the methodology that you are gonna employ to train, and then measure the performance of that methodology. In this case, we are going to use neural nets first. So let's look for neural nets. We'll take the training to the training port and model to the model port. Next, similar to predictive analytics, you have to apply the model. You have to apply the model that is constructed using your training data into your testing data. We connect the model and we connect the test to the unlabeled. Remember, when you use one of the partitions or one part of your dataset, your training dataset as testing, you are going to remove the label, and thus it's going to be that part that is used for testing is going to be unlabeled. The next step is to calculate the performance of this applied model. Let's go ahead and search for performance measurements and performance operators. As you can see, we have few different performance operators. We have performance classification, we have performance binomial classification, performance regression, cost, ranking, support vector, and attribute count. Performance regression is essentially a numerical or a continuous performance measurement operator. Now, what is our dataset? Remember, the dataset is coming from the previous example, the neural nets example. And in that example, we were trying to predict team value for players. And we had different team values. We had superstar, we had contributor, and we had 2 more. So basically, this is a classification problem. You are trying to classify. and we had 4 categories or 4 classes. So what sort of performance operator should I use here? Alright, it's the performance classification. You connect the lab to the lab and performance to the performance. Now we are done with the sub processes. What we did in the sub processes, we told the cross validation operator to use neural nets on the training parts and then apply that neural nets, the created model using training parts, onto the testing part, and then go ahead and measure the performance using the performance classification operator for the measurement. Now before we can run this model and get our results, let's go back to the upper processes, to the main processes. You can see this process is still not connected to the results, so you'll have to connect it to the results. We get the model port, basically it will pass through the model. If you get the example port, it will pass through your example set, and then we get the performance port to the results, which you will get the performance measurements. Now you can go ahead and run the model, but before doing that, just let's take one more look at cross validation. I click on it, and on the parameter side you can see that the number of folds is equal to 10. It means that it is going to divide your data into 10 parts and use 9 parts for training and 1 part for testing, and then it will continue this process until all parts are used for testing. Let's go ahead and run this model. As you can see, it'll take a little bit more time than usual because it has to run the model at least 10 times. Now here are the results. So you get the overall accuracy as 60%, 60.85, and you'll get a range plus and minus 7.9, and that's because we are doing this for 10 times, so each time I'll come up with one accuracy reading. So this 60.85 is that average, is the aggregated average of all those 10 readings, and plus minus 7.9 is the range. And then you can look at the class precision. So class precision, as you remember, referred how good your algorithm is in predicting these classes. The class precision for superstar is 60%, for contributor is 57%, for franchise player is 50%, and for role player is 75%. So what does it tell you when it comes to franchise player? It means that if you suspected a player is a franchise player, this algorithm would give you similar odds as you flip a coin for it. So it's not very accurate. For superstars, it's a little bit more, and it does really good for role player. So when it comes to role players, your algorithm, or you can say that relying on this algorithm, you will get 3 out of 4 chance of being right about some person being a role player. Now let's take a look at the recall values. The recall value for superstar is 48%. It means that your algorithm were only successful in identifying 48% of the superstars correctly. It's 55 for contributors, is 62 for franchise players, and is 76 for role player. And unlike the example that we went through in the lecture, this training data is very well balanced. It means that we have similar numbers or close to equal observations of each of these classes or categories in our training data. So you know that if you use this algorithm for identifying role players, you probably can get good results, but you cannot really rely on it so much for identifying other types of players. And overall, it is only accurate in 60% of the times. It means that it is wrong in 40% of the time. So going back to what I've been repeating, you should never ever completely rely on the results of a predictive analysis. There are so much errors, there's so much inaccuracy. So you will use these results as just some extra points, some extra piece of information to help you or your supervisor to make a better decision. Now let's go ahead and do another example. This time this time for a non-classification or a regression. Let's go back to design, and this time I'm going to drag and drop the file we used for the regression, linear regression analysis. It was the heating oil example in which we want to predict the heating oil usage for a new market. We are going to use the training part only. I'm not deleting my old model. I'm constructing a new cross-validation model for my linear regression. Let me go ahead and rename this to regression training. Okay, I'm going to use a cross-validation. And this time I'm going to get the model, example set, and performance, and then I'm going to go to the next level for cross-validation. For training, this time we are going to use linear regression. I'm going to use apply model to apply the model to the testing part. And then now I have to choose a performance measurement. So which one I'm going to use? I'm going to use regression here because we are using a continuous target variable, and the regression, the performance for regression will give you a measurement for continuous target variable. Remember, for the linear regression we had couple of measurements, we had couple of things that we could look at to understand if this is a good regression model or not. One of them was R-square, which this performance regression will not give it to you. Another one was RMSE, root mean square errors. And as you've learned, the RMSE can be used to get an understanding of the performance of any methodology that you are using on a continuous target variable. Let me connect this, and now let me run this. Again, it'll take some time because it also is running that cross-validation for our neural nets. Here is our root mean squared error, which is 23.86. So as you've learned, this one is scale dependent, and considering the scale, the lower the number, the better. And you can go and take a look at the performance there for the neural nets as well. We use the classification on the team value dataset. Now, as you've learned, neural nets can be used on continuous target variables as well. Now let's go ahead and use the same training dataset for both of these. I'm going to make a copy of the regression training data, which was our heating oil dataset. And connect it here. To reduce the confusion, I'm going to change the name. This one, regression training used in neural nets. Now let's go to the cross-validation, and let me change the name of this one, this operator as well. I'm going to go with CV neural nets, and I'm going to change this one to CV regression. Let's go to the sub-level of the CV neural nets. As you can see, we have an error here because we are using a performance measurement that is designed for classification. Right now, our data set does not have a categorical target variable. It has a continuous target variable. Let me go back. Here I'm using the regression training data set, which was the heating oil example in the neural nets context. I want to model it using neural nets. Now, since my target variable is not categorical anymore, I cannot use the performance operator for the classification. I have to replace it with the performance regression. Again, here RapidMiner call it performance regression, but really what it does is a performance for methodologies that are used on continuous target variable. It's a continuous target variable performance. Now, why I'm doing this? Let's go back. Here you can see that I have modeled my data in two ways. One way I'm using neural nets, and another one I'm using regular regression. So what I want to do, I want to see which one of these are a better methodology, which one will give us a better performance reading. Now let's go ahead and run this. It is already done with the regression, but the neural nets will take a little bit more. So the second performance was the regression performance. You can see that the RMSE is equal to almost 24, and if we go to the performance vector out of our neural nets, you can see that it is 15. It means that the predictions out of neural nets technique on this dataset contains less error compared to regression. And this is how you can compare two different methodologies on the same dataset. You can use this, you can do the similar thing on two different classifications. We could go ahead and use decision tree on that team value dataset. So we could compare whether neural nets are doing a better prediction for our team value, or decision tree was doing a better prediction on our team value. Okay, please let me know if you have any question, and this concludes our tutorial on cross-validation.